Welcome to this explainer. Today, we're taking a seriously fascinating look under the hood of one of the largest tech platforms on the planet. We are going to unpack exactly how Uber scales generative AI. Now, to make sense of their massive, highly complex back-end infrastructure, we're going to use a pretty relatable analogy throughout this whole thing: a high-end, high-volume restaurant kitchen. We're going to look at the recipes they use, the ingredients, the head chefs, and the heavy-duty, industrial appliances that make the whole operation work. Let's get into it.
Think about the last time you opened the Uber Eats app. How does it always seem to know exactly what you're craving? Or, when you interact with an Uber customer support chatbot, how is it so incredibly responsive? While the magic behind these features relies on highly optimized large language models, or LLMs. But here's the kicker: they aren't just off-the-shelf generic models. Uber takes these models and fine-tunes them on absolutely massive amounts of their own domain-specific data to make them incredibly precise for you, the user.
Okay, let's dive into this and peel back the onion a bit. Here's our 6-step agenda for today. We'll start with AI at Uber's scale, look at open-source models, explore the infrastructure stack, outline the distributed pipeline, talk about optimizing for maximum speed, and finally, wrap up with how they actually evaluate these LLMs.
Starting off with Section 1. AI at Uber scale, and how exactly they handle massive global traffic.
You really have to remember, Uber isn't just generating a few text prompts here and there. They're handling a staggering volume of global traffic, for everything from localized search recommendations all the way to automated code development and SQL query generation on the back end. To handle this, they use a technique called Retrieval Augmented Generation, or RAG, along with a ton of fine-tuning. By injecting the models with Uber-specific domain knowledge, think thousands upon thousands of specific items, local dishes, and restaurant menus, they create highly tailored models. And the result? These fine-tuned in-house models can actually match the top-tier accuracy of giants like GPT-4. But crucially, they are built to survive the sheer, unyielding scale of Uber's global traffic without buckling under the pressure.
So, we know the immense scale of the meal they need to cook. Let's move to Section 2. Open-source models.
Here, we really have a tale of two approaches. Now, while Uber definitely does use closed-source models from providers like OpenAI and Google for certain applications, the real secret sauce to their massive in-house operation is their embrace of open-source models, like Meta's Llama 2 and Mr. AI's Mixtral. Why go open source? Well, they're highly flexible, they're inherently secure because the data literally never leaves Uber's ecosystem, and they're incredibly cost-effective. They allow Uber's engineering teams to prototype and build generative AI-driven services so much faster and cheaper than if they were just relying solely on third-party APIs. It's a real game-changer for them.
Let's peel back another layer. Step into Section 3, the infrastructure stack, or as we're calling it, the AI kitchen.
Uber's infrastructure stack is rigorously tested and built out in 3 distinct layers. Conceptually, think of Layer 0, the hardware, specifically those high-end NVIDIA A100 and H100 GPUs, as your massive industrial-grade stoves. Right above that, Layer 1 is orchestration. Using systems like Kubernetes and Ray, this layer acts as the head chefs, dynamically directing traffic and resources to exactly where they're needed in the kitchen. Finally, Layer 2 is federation. Think of this as the restaurant manager. This layer oversees multiple clusters, so essentially managing multiple kitchens all at once, scheduling workloads based on overall resource availability.
And just to really ground us in the staggering scale we're talking about here, consider the specs for a single Google Cloud host used in that Layer 0. We're talking almost 2,000 gigabytes of CPU memory, 8 H100 GPUs, and 6 terabytes of SSD storage. That's on a single host, and Uber runs massive clusters of these machines. To put that into perspective, it is just an unbelievable amount of raw computing power.
With those industrial stoves blazing, let's look at Section 4, the distributed pipeline, where we actually start cooking the data.
This is the journey of a data point across 4 distinct stages. First up, Raytrain initializes the communication across all those massive GPUs so they can talk to each other. Second, the data is fetched, grabbing ingredients from local storage or Hugging Face public datasets. Third, the actual cooking happens. Here, the text is tokenized and the model is trained. Now, notice the mention of PyTorch and DeepSpeed here. These are the specific deep learning frameworks and optimization software suites, basically the advanced cooking techniques, applied to the data. Finally, the finished weights, the perfectly cooked meals, are saved out to TerraBlob, which is Uber's custom storage solution.
But having huge GPUs isn't enough if you don't use them right, which brings us to Section 5, maximum speed and preventing bottlenecks.
Now, what's really interesting about this is how they measure efficiency. To understand optimization, we've got to define a core metric, model flops utilization, or MFU. In plain English, this is basically just how much of your hardware's theoretical maximum power you are actually using. Uber found that while lightweight fine-tuning techniques like LoRa use way fewer GPUs, the accuracy just isn't as good as doing a full parameter fine-tune. But full parameter fine-tuning is incredibly heavy on the system. So to get the absolute best model accuracy without completely breaking the bank, Uber has to obsessively optimize their MFU.
So how do they actually do it? Well, the transformer architecture inside these LLMs has a self-attention mechanism that is notoriously memory-hungry. It scales quadratically, which is a nightmare for memory. Uber uses two main weapons to fight this. First, deep speed 0-3 CPU offload. This basically shifts some of the memory burden completely off the GPU, giving them a 34% reduction in GPU memory usage and letting them push their batch sizes 3 to 4 times higher. Second, they use an algorithm called flash attention. This streamlines that complex self-attention mechanism, saving a massive 50% of GPU memory and allowing them to double the batch size. It's incredibly clever engineering.
And this brilliantly illustrates the real nuance of AI engineering. Uber discovered that not all models bottleneck in the exact same way. When they were training the massive Llama 2 70 billion parameter model, it was what they call memory bound, meaning it literally ran out of memory before it ran out of processing power. So for that one, the CPU offload trick worked best. But when training the smaller Llama 2 7 billion parameter model, it was compute bound. It had plenty of memory but needed more sheer calculating speed. In that scenario, CPU offload didn't really help, but flash attention was the absolute magic bullet. It proves you have to tailor your optimization to the specific model you're cooking.
Okay, the models are fully optimized and trained. Let's zoom back out and move to Section 6, evaluating LLMs. You have to test the dishes before they leave the kitchen, right? So Uber built an in-house offline LLM scorer. This system allows them to run batch predictions on massive datasets to grade their models. By using Ray to automatically create multiple instances on Kubernetes, they can parallelize the entire workload. They split massive datasets into chunks and score them simultaneously using VLLM inference servers. It is essentially a highly efficient taste test, but happening at a mind-boggling industrial scale.
And here's a fun fact from those tests. When running scoring tests on the Mixtral 8x7B model, they hit a really critical hardware benchmark. The newer H100 GPUs achieved a throughput exactly 3 times higher than the previous generation A100 GPUs. 3 times! This kind of hard, actionable data is exactly what Uber's teams use to make their big production decisions and plan out future resource budgets. All right, let's summarize all of this and look at our core takeaways. First, if you want to keep up with the blinding, rapid-fire speed of generative AI, embracing open-source models is absolutely essential. Second, standardizing and obsessively tracking that model flops utilization, or MFU, is really the only way to maximize the massive financial investment of these GPU clusters. And third, having a long-tested, highly reliable cluster management system, those Kubernetes and Ray head chefs we talked about, means that when a shiny new, better open-source model drops, Uber can integrate it into their kitchen almost instantly.
And that leaves us with a final thought to chew on today. Uber is already preparing for the next big wave. Things like Llama 3's staggering 450 billion parameter model. These models are only getting bigger, hungrier, and more complex. So taking these scaling principles and lessons from Uber's infrastructure, how will your tech stack, your team, and your architecture handle the heat of the ultimate AI kitchen? Thanks for joining me on this explainer, and keep building.